All right, so 1.5 is called continuity continued. Yeah. And the IVT, which is really the kind of the more important thing here. So the first part of this is going to be really, really easy, very, very intuitive. We've been talking about continuity at a single point. And what are the three qualifications? Yeah, you can use the analogy, road, bridge, road. Limit from the left, function value, limit from the right, all have to exist, all have to be the same. Well, now we're going to be talking about continuity over intervals. And by intervals, we say x intervals. We always read a graph like a book from left to right and cover to cover. So here's an example of a continuous function, right? You draw it from left to right. There's no lifting of the pencil. Here, no surprise, is a non-continuous function. It has two discontinuities, namely what types? A jump and a VA, right. Are those two removable or non-removable? They're both non-removable. Okay, cool. So, again, it's easy to see those graphically. We want to figure then out analytically from the equation where is the function continuous. In that case, what intervals is this continuous? So a function is continuous at a point, again, if the limit from the left equals the function value equals the limit from the right. Let's go ahead and review just real quickly. I know we just ended this section, but determine the values for which this function is continuous, and then some bonus questions. So kind of like the pre-response that we just worked. All right, first things first, if you missed this on the test, look at your pieces. The top piece right here has a built-in discontinuity, does it not? At x equals what? -3. There's a who? Whole or VA? There's a VA, right? Remember rational functions, polynomials over polynomials, which includes constants over polynomials, are going to either have wholes or VAs. So this is a VA at -3. Is it even relevant? Are we even defining that function at -3? By that piece. Yeah, we're defining it to the left of -2. So we know that x cannot equal -3. It's relevant. But the other pieces are a line, parabola, and then the square root of x only lives for positive x values, and so we're way out to the 4. So it's continuous over its domain. So that's the only one that's a built-in discontinuity. The only other places to check then are at -2, 2, and 4, right? Now, I'm going to spare the all the cumbersome notation, okay, because we just did that. So let's just kind of do it mentally in our head. Is the function continuous at -2? Well, the limit from the left to -2 is what by direct sub? 1, right? You plug a 2 in, -2 in for x, and the 1 over x plus 3, you get 1. The limit from the right to -2 and the function value are the same because it's less than or equal to x. So by direct sub, you get -4 plus 5, which is 1. Okay, does 1 equal 1 equal 1? Yes, so it is continuous at -2. So I'll just put yes. All right. What about at +2? The limit from the left is 4 plus 5, which is 9. The limit from the right of 2 and the function value of 2 are 2 squared, which is 4. Does 9 equal 4? No. So x cannot equal 2. There's a discontinuity. Not x cannot equal 2. I'm sorry. I'm listing discontinuities at x equals -3 and 2. So we have a VA at -3. What type is there at 2? There's a jump. Good. If the limits exist but they're different, there's a jump. So 2 is no good. What about at 4? The limit from the left of 4 is 16. The limit from the right of 4 is the square root of 4, which is 2 times 8 is also 16. Is this function continuous at 4? No, this is the one where I'm trying to trick you, right? It's not defined there. Very good. It's not defined at 4. It's strictly less than on one side, strictly greater than on the other. So the limit exists, right? The general limit at 4 does exist, and it's 16, but there's no function value. There is no bridge. So what type of discontinuity do we have at 4? There's a hole. Okay. So we could say then that if we're talking about intervals, f is continuous. We could say for all x, which we imply are real numbers, not equal to -3, 2, and 4. So that's not really expressing intervals, but it's kind of saying the same thing. It's kind of like set notation. Here's where it's not continuous, therefore it's continuous everywhere else. All right, and then bonus questions. What's the limit as x goes to -infinity? Which piece are we using for -infinity? The top. What would be the limit as x goes to -infinity then? 0, right? Good. The top is a constant. The bottom gets really, really big. And we could determine if we're approaching 0 from above or below. Well, we won't. What's the limit as x goes to +infinity? Which piece? The bottom. So what's the square root of infinity times 8? Infinity, yeah. So this one's going up forever to infinity or dne. Remember, on a free response, that would work. All right, so there's review, right? We viewed again. We reviewed it. All right, so now let's define continuity on an interval. You're going to like this definition. A function f is said to be continuous on an interval I. We use I for an interval. It could be open, closed, half closed. If and only if the function is continuous at every point on the interval. All right, we usually talk about an interval like this. We say from A to B. And you have to use context clues because that would be an open interval from A to B, and it sure looks a lot like an ordered pair. So if it talks about an interval, these would be x values. Okay, you can also put x epsilon in front to help people distinguish that it is not an ordered pair, but an interval from x to b, from x equals a to x equals b. And of course, the way we write intervals, a is always less than b. We always list x values from least to greatest from left to right. All right, so that gives us a way to figure it out, right? If it's continuous at every single point on the interval, it's going to be continuous on the interval. So how many things are there to check for each point on the interval? What definition did we just talk about? The three-step definition, right? Road, bridge, road. So if we could check that at each and every point, road, bridge, road, at each and every point, we check three things. If it passes for all the points, it's going to be continuous on the interval. So that's pretty cool. Let's see. How many points would there be then on any given interval from A to B? Infinitely many, right? So with infinitely many points and three things to check per point, that would be 3 times infinity or infinitely many things to check, right? So is that how we're going to be checking for continuity on an interval? Doing a three-step definition infinitely many times? No. You know how we're going to do it? It's going to be a lot easier. We're going to use these guys, our peepers, right? We're going to give it the old eyeball test. We're just going to look. We're going to look at the graph. We're going to be given a graph, and we're going to look to see if it's continuous on an interval, okay? So that's it. More specifically, a function is said to be continuous on a closed interval or on an open interval, a, b, if and only if it's continuous at every point on the open interval, and it's continuous on the closed interval if, and this is important, it's continuous on the open interval. Okay, that's important. So between A and B, there's no breaks, gaps, jumps, or holes. But we only have to look at the three-step definition, 2 criteria. Okay? At the left end point, we only have to say that the road coming in from the right and the function value are the same. Okay, so this would have to be connected like that. We don't have to look to the left for the left-sided road. And for the right endpoint B, we only look at the road leading in from the left and make sure it's the function value. So this kind of loosens up the 3-point definition of continuity at a point. If it's an endpoint of an interval, whether the function is defined to the left or not, if we define it on a closed interval, we do not care about the left values to the left of A or the values to the right of B. Okay? We only do 2 of the 3 steps. That's important. So this thing would be continuous on the closed interval. All right? If we had something that looked like this, would that be continuous on the closed interval? No. So we could write this one like this on the bottom. We would write that A, comma, B with brackets. So that one would be continuous at the right end point, but it would not be continuous at the left end point because the function is not defined. What if I define the function value right there? Does that make the top one continuous now in the closed interval? No, because now the limit from the left and the function value are not the same. So we could still say that this one up here would be continuous on this interval. We could call that the half, what? Half closed if we're a pessimist, right? Or a half open if we're an optimist, right? Half full, half empty, right? It doesn't matter. You're not a pessimist, though, right? You were just playing devil's advocate there. Yeah, good, yeah. You don't strike me as a pessimist. I don't care if you say half open or half closed, and I don't know if there's any truth to that, like pessimists say half closed. What's that? Too big of a cup? So we can define things. We don't have to say it's either closed or open. We can define it as half open, half closed. All right? So let's look at example 2 right here before lunch. In the graph of x given below, determine the largest intervals from 0 to 3. Okay, another way that closed interval could be given to you is like this. So we're looking on the closed interval only from 0 to 3. for which the function is continuous. Let's just go ahead and start listing it from left to right. It says to list the largest intervals. So is it continuous at the left endpoint, 0? Yes, we don't have to look to the left of 0 because 0 is a left endpoint, so we'll say it's continuous at 0. And now we cruise till we get to our first discontinuity. Is it continuous at 1? No, so we'll put comma 1 with a parenthesis, and we'll step over 1. Where's the next discontinuity? 2, open or closed? Is it continuous at 2? From the left it is. Very good. So it is closed. Kevin, you are right. See, that's what's different. As we're approaching 2 on the interval from 1 to 2, the right-sided limit at 2 is the same as the function value. So it is continuous at 2 from the left-hand side. Union, is it continuous at 2 from the right-hand side? No. So we put parentheses and then we cruise all the way to where? 3 with a bracket. Yeah. Now, I just stepped over 1. I put parentheses on both sides. I should have probably talked about that. But notice that as we approach 1 from both sides of that interval, it's non-inclusive, okay? So that kind of makes it a little bit different, or it could be included on one side but not the other. And that was easy because we're just using our old what? Peepers. We're using our peepers, our eyeballs. We're getting the old eyeball test. So this function, whatever its name, function f, we could say f is continuous on, and then we'll just list that right there. So if we don't put x epsilon, but we're talking about intervals, are those x values or y values? X values. It is understood that these are always x values. We always list x intervals. They are independent variable, and we always list them from left to right. Okay, have a good lunch. We'll pick up with example 3 after lunch. Eat some carrots. It's good for your